Okay, well, welcome back to Math 423. We're going to continue our development of sets today with a brief review. So, if A and B are sets, the thing that qualifies a collection of things to be a set is simply, can I absolutely for any element distinguish membership or non-membership? Right, we say X is an element of A. If it belongs in the set, if it's a member of the set, and we say X is not an element of A if it's not in the set. So that's the basic idea. If I can do that for any X, then I have something that's well defined as a set, and then we discuss that A intersect B is the set of all X, where X is in both of them. Or in Venn diagram notation, just tiny Venn diagram notation, the intersection is the overlap, right? And A union B is a set of all X such that it's either in A or in B. And when we use this mathematical logical or, we mean in A or in B or in both. We always, it's called the inclusive or, we always include. So in this case, if this is A and this is B, we want it all. Right? A, B, and the overlap is the or. And then A minus B was the other big thing. The set difference, A subtract B is the set of all X, such that X is in A, and what? It's not in B. So we could do it this way, or we could say that X must also be an element of what, if it's not in B? Must be in the complement of B, right? B bar or B. That's the same thing as saying it's not in B. Okay, so that's all review. Where I want to go today is review the rules for set equality, give some examples of set notation, look at the algebraic properties of sets, that is how do and or and complement behave, look at how to prove set properties, which you need for some of the homework that you already have assigned. We'll look at the Cartesian product of sets and also what a power set is. So it's going to be finishing up coverage of all the material in our set chapter. So let's move forward. Now that we have our basic set operations, remember two sets are equal under what conditions? What do we need to be true for those two sets to be equal?
They're both subsets of each other.
Yeah, that's the precise definition. If and only if A is a subset of B and B is a subset of A. What does that mean? It means that X in A implies X is in B. Right? That's what this means. And X in B implies, yeah, this is functionally how we actually do this. We pick an arbitrary element in the first set and demonstrate that it must be a member of the second set and vice versa. We have to prove both of these to prove set equality. So a trivial example of this, of equal sets and set notation, This one I kind of like. For finite sets, we can sometimes list them in order. List all the elements if it's small enough. That's the same set as the set of all x in the natural numbers, such that x is less than 4, according to our textbook. In this class, by convention, I guess, we'll include 0 in the natural numbers. That's not well defined. So, what do I do? It's real easy. I look at each element here. Is 0 a natural number? Yes. Is it less than 4? Yes. So it's here, and I can walk them all this way. I can look at each element individually and show that it satisfies those properties. It's a little more challenging to go the other way. Pick an arbitrary element less than 4 that's a natural number. It's pretty easy to see it must be one of those. So those sets are equal. So now I start out with a giant set, the real numbers, and restrict it to those that satisfy an equation. Now those two sets are equal, because what are the only two values that satisfy that equation?
Square root 2.
It's a negative square root 2, right? And it's a quadratic equation. We know it has exactly 2 roots, so it's easy to see that those are equivalent sets. Okay, just one more for set notation. A real pretty one, I think. I'm going to write it over here. The rationals are the set of all x's in the real numbers, such that, just to introduce some notation, just to introduce some sort of ugly notation, right? The set of all rational numbers such that there exists a pair of integers, I guess I have to put these in Z technically, a pair of integers where m is bigger than 0, and by multiplying that number by this integer, I can get another integer. Well, isn't that sort of clear once we read it that way, that that's a description of fractions? What is this operation? This is nothing but clearing a fraction, right, by multiplying by its denominator. So if I can get an integer by multiplication by an integer, then the thing must have been a rational number, otherwise not. I can't multiply pi by any integer and get an integer. I can't multiply the square root of 2 by any integer and get an integer. But if I have a rational number p over q, what do I multiply it by to get an integer? Q, right? I multiply by q, and this is p is an integer. Right? Okay. So that's a little bit of set notation and the idea of set equality. I want to now go to the kind of the new meat of today's material, which is what are the properties, the algebraic properties of these operators, and, or, and set difference. Change color for this, that would be nice. Okay. So if A, B, C are sets in a universe, so we can say it this way. Subsets of some universal set, like they could be subsets of the reals or subsets of the integers or subsets of any set that kind of describes the world we're working in. Then we have the following properties. that should go almost without proof, right? Because the element's in here. If an element is in this guy, it has to be in both A and B. If an element's in here, it has to be in both A and B. It's because the logical operator and is symmetric, so that's true. And similarly, A union B is the same set as B union A, and we call that property commutative. Yeah, these two operators are commutative. Property 2. If I intersect A with the intersection of B and C, I get the same result as taking A intersect B and then intersecting it with C. An easy way to see that with a picture that you have in front of you. If I call this set A, this set B, and this set C, where is AB? Well, AB is, A intersect B is here. And if I intersect that set, A intersect B with C, where do I end up? I end up there. If instead I take B intersect C first, I end up in here. When I take B intersect C and intersect it with A, I'm back in the same place, right? It's just the intersection. And this is almost the same way you would prove it with element by element. So what do we call that property? Associative. And it's true also for union. So it doesn't matter how I group the operators, and then by extension, with a little inductive proof, you can show it works for any number of symbols. So both operators, intersection and union, are commutative and associative, and Venn diagram reasoning kind of helps you see how to prove it if you have to prove it. Okay, the next one is really important. Next pair of properties. So if I first take the intersection of two sets and then form the union with another set, the claim is that's the same as taking the union of that set A with both of them individually and then taking the intersection. What is that called, a property like that? Distributive, yeah, that's a distributive property. In this case, that union distributes over intersection, and there's a mirror image to this. I'll just write the mirror. Make sure I get my symbols right. So intersection distributes over union, similarly. So these basic properties let me do algebra, right? I can distribute things, I can change the order of things, and it doesn't matter how I group things. It gives me a setup that I can solve set equations with algebra. But I need a couple more properties, so I'll let this dwell for just a second. Maybe it's worthwhile doing a picture. another three-ring picture. If I take three sets, A, B, C, A green, B red, C blue, let's reason through this first rule. Where is B intersect C? Well, B intersect C is that piece, right? If I form the union of that with A, I end up with this monster. That's A union B intersect C. Let's draw it the other way. Yeah, this side. So I can keep them both up there. The box, of course, represents my universe. What does the other side say? It says, take the union of A and B. So that's all of this. And also the union of A and C. A, yes, A and C. Right? And form the intersection. Well, where is the intersection of those unions? Well, both of them have all of A and C. So, there. So we end up with the same set. The outline is going to be up to C, around C, and back to A. The exact same shape we have there. So that's a graphical way of reasoning. We'll look at algebraic way of reasoning in a minute. Okay. Two more important rules of set algebra. If I take the complement of the intersection of two sets, it turns out what I get is the complement union the complement. And if I take the complement I get the intersection of the complements. These are called DeMorgans Laws or DeMorgans Rules, and they let me manipulate complements or inversion. Remember, the complement of a set is just the universal set. Subtract off A, and what's left is the complement. Well, how does a Venn diagram help me in this case? A lot easier to draw with just two sets. So let's take our universal set and take two sets A and B. So what does the complement of A intersect B look like? Well, where's A intersect B? It's the little part in the middle, right? So its complement is everything else. Everything else. So I have the complement of A intersect B is everything except that little piece. Let's draw the other picture. Universe B with A. And what if I take just the complement of A? I'm going to draw that as my green. So my green is A complement, everything that's not A. And if I take the complement of B, I'll draw that as red. And there's everything that's not B. If I form their union, what's the only part that's not covered? Exactly what we have, right? So there's a graphical proof of the first of DeMorgans Laws, and the other one goes pretty much as follows. Okay, two more little things. Let this dwell just for a minute. Where we're going is because we have commutativity of properties, associativity of properties, we know how to take complements. It almost sounds like we're heading for a field again. It turns out not, but we're pretty close. So the last two properties. If I take the union of A with its complement, what do I obviously get?
Everything.
Everything. I get the whole box, the universe. And if I take A and union it with the empty set, what do I get? A, sure. Because I add nothing, right? Adding nothing is nothing. Remember, union is an or. It's going to be in the union if it's in here, or it's in here, but there's nothing in there. So, and then for intersection, if I intersect the set with its complement,
Also.
a null set, sure. Because there's nothing in the intersection by definition. Because the elements in here are precisely those elements that are not in the original set. And finally, if I take A intersect the universe, I get A. I think I did this, but, and then if I take A intersect the empty set, the empty set, of course. So that kind of completes that. But now, what do we have? This is the killer. Let's look at intersection. We know intersection is commutative, associative. Is there an identity for intersection? What set intersected with any set leaves it alone?
Intersect with the universe.
The universe, sure. So the universe is the identity. And what else would we like to have happen? does every element have a inverse, right? Well, to be an inverse, if this is the identity, I need to take the set A and intersect it with something and get the universe. Will that work? Is there any set? I take an arbitrary set A, I want to intersect it with something and get the universe. Is that ever going to work? No, it's not going to work. Doesn't work. So I don't have all the nice properties here. Almost all of them. Commutative associative identity, but no inverses.